Yes, I should be. Good Lord, what is happening in there?
Aurora Borealis?
Aurora Borealis. At this time of year, at this time of day, in this part of the country, localized entirely within your kitchen.
Yes.
May I see it?
No.
Welcome to the Expanding Universe.
I'm Ryan Marciniak.
I'm Jesse Robertson.
Let's get right to it. Yeah, let's talk Aurora. I thought about this story because a couple weeks back I got an email from spaceweather.com. I subscribe to their site because it's kind of cool to get random emails about when there's going to be big storms from the sun, and it might be a chance to go out and see some aurora. And I especially did this because I was up in the Yukon last summer, and I wanted to know, like, if there's going to be a storm, I want to be able to see some aurora while I'm in the Yukon. And unfortunately, as we'll get into, I was there in July and August, and
when there is never night.
There's no night. There's no night, and the auroras are typically a lot weaker at that time of year. The peak season is kind of September through to November, December, even January, and then it kind of peters off. So, but the reason that I wanted to talk auroras specifically is that I didn't realize that you could have an aurora without a sunspot. See, so my understanding for the longest time is that, the sun, and most of this is true, is that the sun is constantly streaming out these charged particles. The sun is a giant nuclear reactor, basically. I always tell kids it's like 1 million nuclear bombs going off every second. And,
that sounds safe.
Right? Exactly. So it's constantly streaming out these charged particles, electrons, protons, alpha particles, which are helium nuclei, right? 2 protons, 2 neutrons, and they're just all firing around in all directions. And so those particles, they hit the planets of the solar system naturally. They arrive at the Earth, and generally they're very bad for human beings. They can damage our DNA, cause mutations, do all kinds of horrible stuff. Radiation is bad.
No kidding.
Yeah, but luckily we have something that protects us here on Earth, and that's the magnetic field. And so the magnetic field of the Earth funnels all those charged particles up to the North and South Pole. And when those charged particles finally do penetrate the magnetosphere, come into the atmosphere, they energize some of the molecules in the air, and excite them, get the electrons boosted to a higher energy level. And then when the electrons come back down, they calm down, they release some light. And so essentially what happens is that in that interaction, you produce different colored light based on the different molecules and the transitions, the electron transitions that are happening in the atmosphere. So that's the aurora. And I always tell people, I say, if you can see the northern lights, the aurora borealis, it means that the sun is not killing you. Because basically that's what it means. It's like, yes, the Earth is protecting us. I can see the aurora. But if you don't see the aurora, there's trouble.
The sun is not killing you.
Right.
I like it.
Yeah. So and that one's always fun because then the kids are like, "What? We're not? What? Like, whoa, we could die from this? Oh my god!" So and then it comes this whole discussion. So, but the thing that I thought is that you need sunspots, which are kind of magnetic knots on the sun, and it results in cooler areas. And we see these sunspots as dark spots on the surface of the sun, and they tend to release a huge amount of solar wind. And so typically when you have a sunspot pointed toward the Earth, you can get a lot more discharge of solar wind, and 36 hours later, after it travels the 150 million kilometers from the sun to the Earth, we start to see more aurora or stronger aurora. And so that's generally it. That's how you see a solar storm. Space weather sees it. The SOHO satellites up in space see it, NASA satellites. Space weather sends me an email and says, hey, in a couple days, there's going to be some aurora. And
the universe lets Ryan know.
Yeah, and I somehow prepare and get there and don't actually see it because it's cloudy. So
Southern Ontario.
Right? But the thing that really drew me to this was that I got an email from Space Weather a couple weeks back, and they actually said that there's a huge chance of auroras. There's a huge amount of solar wind coming from the sun, but there were no sunspots. And so my question was, how do you get a big solar storm without sunspots?
And I wish I knew the answer to that.
Well, and
I'm thinking
apparently
you just need an active. Let me guess. You just need an active surface. You need the atmosphere of the sun to be more active than normal. That it would kick away a lot of stuff, and you would need the magnetic field of the sun to allow it to happen, because the magnetic field of the sun is pretty intense and holds on to material pretty strongly. So you need to have because a solar flare is what causes our aurora normally through the sunspots, and that's happening when you have the sunspot sort of doing something magnetically weird, and we'll get into that. I have a question for you on that. And the magnetic field eventually lets a bunch of material go. So you need that happening without a sun. I have no idea. I'm trying to talk this through. I have no idea why that happened.
Well, you're on the right track, though. You said that there has to be a larger kind of flux of charged particles from the surface of the sun, and that does happen. But it's because there's essentially a gap in the magnetic field, right? The sun's magnetic field is constantly interacting with itself. The sun spins every 30 hours. So
no, it's
is it more than that?
It's no longer than that. It's once every 30 days.
Oh, 30 days. Okay.
Yeah.
I don't know. I thought maybe it's Jupiter. It's 30 hours. So 30 days, right? And so, I mean, for the sun being gigantic, that's still pretty quick.
It is super fast. Yeah.
Yeah. And so, you get the magnetic field is getting bunched up, and there's huge interactions with the plasma of the sun. And it's this wild
plasma
thing, right? And so there are actually times where the magnetic field has kind of pulled away and created a gap where the stream of particles can just come straight out from the surface, and that was what caused it. That was basically what created this magnetic storm. And actually, I got an email just today of the exact same thing. There's a G1 and G2 class solar magnetic storms, and there's no sunspots, and there haven't been sunspots for the last 6 days.
So let me get it straight. So it's kind of like this. So the magnetic field of the sun, you can sort of picture as an invisible net, really fine, thick net that those are two words that are opposites. A really thick net over the sun that sort of holds in the massive atomic bombs that are happening every second on the surface of the sun. So you have all this material that wants to blow away from the surface, but the magnetic field is holding it there because magnetic fields hold and capture charged particles. Now, because the magnetic field of the sun is so turbulent, because the plasma of the sun pushes and pulls on it along with the spin of the sun, you can create gaps in the net, which then basically allows you to look directly at the surface, not through this invisible force field that is the magnetic field, allowing massive amounts of material just to shoot out without any acceleration from any other mechanism. It's simply just material flying off the surface.
That was much better than the way I said it, so yeah, let's go with that. Well done.
Well, you're the teacher in this case, so you got to give yourself a pat on the back for that.
I suppose so, but I mean, it was interesting because it's one of those things where you and I have been doing astronomy for almost more than a decade now.
For me, it's about a decade, yeah.
Yeah, so I mean, I'm coming up on 2 decades at this point, but you still learn all these new things. And that's the fun part of it for me, is that astronomy is the science that's still constantly being pushed, and we find new planets. We've talked about some of this stuff before.
The science that keeps on sciencing.
It is the science that keeps on sciencing, because the universe is so damn big. There's always going to be something that's a little bit weird out there for us to look at. And for a few years, it was this like, oh hey, we found a planet that does this, or the first planet that is like this, or it was the planet thing. And now we're kind of getting away from that and getting into like we talked about, gravitational waves, and yes, still exoplanets to a degree, but even the sun It's
There's so many firsts still to happen in astronomy.
yeah, and I love the fact that I can still week to week learn something completely new that gets me really really interested in it. But yeah, Aurora, just really cool stuff. I haven't seen
Have
much.
you ever when was the first time you saw them?
Oh gosh, I was probably about 14.
Oh, you lucky bastard.
I was well, I was at my family's home. Yeah, I must have been 14 or 15. We had just moved into a house in the country up north, about an hour north of Toronto. And I don't know how I found out there was going to be a storm. Maybe I heard it on the news or something. And I
Did
remember,
email exist at the time?
I don't think. Well, I don't know. It's a good question. I think it was start. Yeah, I think it did. But I remember going outside and taking a look toward the north, and there was just this green wavy glow, and I was like, oh, I think that's it. And I was pretty sure because I'd seen lots of photos of it. Although this was right very close to a major city, Toronto, very far from the polar region, very far from the
Was
region.
that like 43 degrees or 42 degrees?
Yeah, exactly. So it was a pretty big storm because I think that was the only time I had ever seen it from that location, from my parents' house. And I just kind of stuck my head out, and there it was, and it was kind of like, okay, that's cool. I'm glad. Like, check that one off. And then actually, when you and I were in undergrad at McMaster in Hamilton,
Yeah.
there was one in our second year, and I remember going out onto the street in the middle of the night to watch it. And even from the city of Hamilton, where the streetlights were really bright, I saw a little bit of it. And I was thinking, oh, that's cool. That must have been a heck of a storm.
No kidding. Where was I?
I don't know.
Playing Nintendo, probably.
Probably, yeah. I think that's reasonable.
So
where did you see it? Yeah, where was your first?
My first
experience?
time was
With Aurora.
Oh yes, with Aurora, with seeing Aurora. Jeez, this is all bad. Was in Calgary. So I lived in Calgary for a year, and this was when I was 30 and 31. So this was the first time was very recent, and me and Alex, my girlfriend, we had been about an hour and a half south of Calgary to visit her family, and it was after dark, and we were driving north home to Calgary. Now, this is in the middle of the plains of Canada, and it's Calgary is very dense. Calgary has a lot of lights, but once you get out of Calgary, it is dark. There is nothing, and we're driving north on this highway coming into Calgary. We're still about 45 minutes away, and Alex goes, "Hey, look, there's the Aurora." And I look and I see in the north these like green ropey curtains that are sort of like twisting and turning. And I look at it, I'm like, no, that's not the Aurora, because like I'm an astronomer in my head, and I would know the Aurora if I saw them. And I like it took me like a good 5 to 10 seconds to be like, holy crap, you're right, that's the Aurora. And they were really fast moving, really quick. They were jumping around. It was like snakes and curtains in the sky, very green. Whitish green, and we pulled over. We pulled off to on a side road, like a maintenance road to the side of the highway, and we just sat there for 5 to 10 minutes and just took it in, because that was the first time I'd ever seen it.
That's cool. But you see, it's interesting that you say it moved quickly, because I've always found that they move very slow. Like, I mean, maybe it's because I see videos from the ISS, or I see people have taken time lapses, which was on my bucket list, to get a time lapse of the Aurora, but it's sped up, right? So you see them kind of really dancing, these big veils that are moving around really quickly, and I think a lot of people have that as their main kind of touch point for what it looks like. So then they get out there and they actually see it, and it's kind of slow, and I think that's how I felt seeing it. Even in the Yukon, I did end up seeing a little bit on my last couple nights there. And again, it was just kind of that slow kind of dance, and you could tell that it was changing. And occasionally, you'd get a big burst of a bright spot that would kind of come up and disappear over 10 seconds or so. And that, but it was much slower than I ever thought it was when I first saw it.
It was. I think there are different mechanisms that cause different types. I think honestly the science of it is still ongoing. I'm not an expert on it, but I'm pretty sure that the mechanism, the direct mechanism, is still under investigation. We know the broad strokes of like what you said at the intro, but I think there are different mechanisms, and one will sometimes will make it go quicker, and some will make it go slower. That also being said, we might be talking about the same speed, and I see it as quick and you see it as slow.
Oh, so, totally. It's very subjective, right? I mean,
yeah.
And that's kind of why I said, the benchmark for a lot of people is those faster videos. At least it was for me anyway. But
it wasn't as quick as those.
Yeah.
That I saw.
Yeah, definitely.
Now that the second time I saw it was also in Calgary, and it was in Calgary and directly overhead.
Wow. So it must have been a heck of a storm.
It was really big. It was Alex and I were like getting ready for bed, and we looked out the window and we saw it, and we like piled on a whole bunch of it was pretty chilly.
Now, was that green? Was it green too?
No, at that time I think that the city lights really drowned everything out, and it was pretty white. It was sort of like grayish white. And it was flickering above our heads, and we had some camp chairs out, and we were just watching it.
Well, you know why it's gray more than green sometimes? Like why? Like
no,
white,
I don't.
There's not. I don't think there's really white aurora, because I believe what's happening is that your eyes aren't picking up the color. It's that the cones in your eyes aren't excited, aren't picking it up. Right? It's the same reason that we see stars in the sky look white as opposed to colorful. Even though most of the stars are red up in the night sky, most of them look white because our eyes can't pick up the color from the dim stars. Only the brightest ones will sometimes activate the cones in our eyes. It's the same reason when you're outside in low light, your night vision comes on and you can see people, but you can't tell what color clothing or anything that they're wearing, right?
Right, yeah.
So I wonder if it's kind of that, because I haven't seen... And to be honest, I haven't done much of the research on it, but I also haven't seen any red or blue aurora.
Nor have I. No, I've only ever seen the green tinge, and it was just that one time.
And I'd love to see red. And I you wrote some notes on the different wavelengths and how you get them, right? Excited atomic oxygen at high altitudes will be red. At low altitudes, it'll be green. From a different atomic transition.
Mm-hmm. Yep.
And blue would be really cool to actually see nitrogen.
That happens. Yeah.
Nitrogen emission. I've seen pictures of blue aurora. I've seen a lot of pictures of red, and a heck of a lot more pictures of green. But blue is definitely the rarest, and I think you only get that when you have those kind of really huge storms that happen at the peak of the sunspot cycle. Actually, speaking of which, what is the sunspot cycle? Do you want to tell us?
Oh, yes, I can. The sunspot cycle. It's an 11-year cycle where the sun goes through a maximum and a minimum phase. Now, this has to do with it's really, really complicated. This was something I wanted to get into, Ryan, is how complicated the magnetic field is on the sun. Mm-hmm. So our Earth has this beautiful magnetic field that it acts like a bar magnet and does very little in the grand scheme of things. It kind of just does. It acts like a magnet. It's very simple. Mm-hmm. On the sun, it has a bar magnet idea where there's a north pole and a south pole, and the field lines go out the north and in the south, or whatever the opposite is. I don't know. But the interesting thing is that the entire sun is a plasma. It is a ball of charged particles, and electric fields, when moving, a moving electric field will induce or create or affect a magnetic field. That's the basis of electromagnetic theory. And so the fact that the sun is just one big magnetic inducer, basically. And so you have this really weird, complicated magnetic field that doesn't go as simple out the top and in the bottom. It loops and it wriggles and it changes and it tightens and it twists up, and as the sun spins, it actually is tightening up that magnetic field. It pulls it drags it around the surface of the sun.
Is that Coriolis force?
It's not the core. I couldn't tell you.
Well, fair enough.
The Coriolis force is related to rotation, so perhaps it's a force, but it's
Don't, I totally derailed you. So just
the point being that the rotation of the sun as a ball of plasma messes up the magnetic field.
Yeah.
And it tightens up and gets dragged around, and then eventually will get so tightened up that it reverses its polarity. And
wow.
That's the whole cycle. And during that cycle, there's this increase of sunspots, and then up until the solar maximum when you have this massive output of solar flares, and then and then it goes down to a solar minimum when you have very few sunspots and very few solar flares. And it's pretty consistent. It's not exactly 11 years every time. Sometimes it's like plus or minus 1 year.
Yeah.
But we've been studying that. I don't know how long ago did we notice that? Like maybe the late 1800s?
So I'm glad you asked, because I was just looking at something that was talking about this being cycle 24. We are in sunspot cycle 24. So presumably it's been a few hundred years.
Yeah,
if
that
you
sounds
look
about
at
right.
10 years, roughly 250 years of maybe data, at least, or even anecdotal observations of.
Well, Galileo was counting the sunspots.
Well, there you go, and that was over 400 years ago, right? So.
It's funny. I learned in prep that Galileo coined the term Aurora Borealis. He named them.
I also had no idea that the sun's magnetic field actually flipped, and that's why you had the cycle.
Oh my gosh. Am I wrong?
You shouldn't. No, because I don't know something doesn't mean you should question what you know. No, you're good. That's cool. I could it totally makes sense. We're good. So let's power through. I want to talk about
Ryan, you're my check and balance. I need you to if you
if we both don't know something, then we have a lot to learn. But
yeah.
I wanted to talk about other planets too, because that was another amazing thing that I learned a few years ago, and I think I really learned it with Cassini, and I learned it with Juno and the Galileo spacecrafts, and especially for me, it kind of solidified when I found out that Ganymede, right, the largest moon in the solar system, has Aurora.
What?
Yeah.
It doesn't have an atmosphere? Does it?
No, it has Aurora. I believe they're induced by Jupiter's magnetic field. Like it's because of Jupiter's effect on Jupiter induces small magnetic fields in Ganymede, and that's what creates Aurora on Ganymede.
No, but see, the thing is you need to have an atmosphere, because the magnetic field is one piece which catches the charged particles, but you need those charged particles to hit something.
Okay, so I gotta look at this. I'm
Googling it right now, and if you're right, I'm just what is it? Must have like it must be like a really, really thin exosphere that just.
Well, it probably does, because Ganymede has a liquid water ocean underneath.
What?
Yeah.
How did I not know that?
It was only a couple of years ago that we found that out.
How many ice water moons are there now?
That would be the third or fourth that I know of, maybe fifth.
Okay, so then if you have this ocean, if you have some ices going on, you have some volatile compounds, and you can get a little bit of it floating near the surface, then you'd have like a very thin exosphere, which if you throw charged particles at, could give you some aurora. They'd be faint, I guess, but.
Yeah, large saltwater ocean affects Ganymede's magnetic field. So the saltwater ocean and the nickel iron core affects gives it a bit of a magnetic sphere, but it's also due to Jupiter's induction.
That's crazy. I would never have expected. Like, you're right. You're totally right. But a place that has no major measurable atmosphere, still able to produce aurora.
Well, and I wonder how much of it is tied to that subsurface ocean, right? Because you look at Enceladus. Enceladus would not have an atmosphere; it's too small. But it has these jets of material coming out from that ocean, these geysers, right? And so Ganymede being the largest moon in the solar system, I mean, heck, it's larger than Mercury is. It should be able to hold on to something a little bit.
Yeah, Mercury would have an atmosphere if it wasn't so close to the sun.
Yeah, exactly, right? So I could see that kind of makes sense. I mean, now the auroras weren't something you would ever see. It wouldn't be anything comparable to what you see on Earth. But, I mean, we know Jupiter has aurora.
Oh, yeah.
And Jupiter has some huge aurora.
Saturn as well. Uranus and Neptune both have aurora. And Venus and Mars.
So pretty much everywhere.
Pretty much So this is why it's what you're saying is surprising me, is because my understanding was that as long as you, like, magnetic field is important, but not the whole story. It's the atmosphere that's important. Because you need something for it to hit, right? So Mercury doesn't have any aurora because there's no atmosphere there because the sun blows it all away. But Ganymede is bigger than Mercury, far enough away that the sun doesn't blow away any exosphere. So maybe there is like this. Even though I bet there's other moons.
There probably are. I could see there being some on Titan. I don't know if there are.
Oh, there would have to be.
Although Cassini spent a lot of time around orbiting Saturn and hasn't.
True.
We found any.
I feel like we would have heard about that. Although the lakes were the bigger story.
Okay. Oh yeah, Ganymede's got a tenuous oxygen atmosphere. Yeah, there you go.
Nailed it.
Yeah.
See, I'm a planetary scientist.
Right. Well, I gotta say, like, planet science has always been the most fascinating one for me. Like, ever since I was a kid, I had books on planets, and like that's what I was interested in more than stars, more than galaxies, more than other things. So I've got a kind of an affinity for what goes on with the planets, and but it is amazing to see. And let's talk about Mars though. How the heck do you get an aurora on Mars? Now, okay, look, let's be honest. We've talked about some reasons why you would, but Mars is missing one of those two big components, right? We said a magnetic field and an atmosphere. We know Mars has an atmosphere, right? Thin carbon dioxide, but clearly a thin atmosphere doesn't stop anything. It doesn't stop Ganymede. But the magnetic field, Mars doesn't have a magnetic field, right? That's why it lost all its water in the first place.
Yeah, you got me. I don't know. Like, I mean, the real key is you need a charged particle from the sun to be hitting the atmosphere of the planet, and that will excite the molecule. The reason the magnetic field is so important is because it concentrates it. It catches all the particles and concentrates them in one spot, and then you get a bunch of it happening, so it's really visible. The only thing I can think of is that you just have a super dense wind that is concentrated in itself before it gets to Mars, and then it like just hits Mars, and then that area that had the concentrated wind would give you light. Okay,
so I do know a little bit of the answer. I was hoping you would fill in some gaps for me.
I did,
but that's okay. You kind of have throughout this conversation, but Mars doesn't have a global magnetic dynamo. It doesn't have a liquid metal core like the Earth does that can create that magnetic field, that moving charge to create the magnetic field that we see globally on the Earth. But Mars used to have this magnetic field. It still has a magnetosphere. And it gets kind of, this is very, very thin, very weak, and I think a lot of it is left over from the solidification of the core. It kind of locked away the magnetic orientation of metals and of I guess molecules in the crust. So Mars has enough of a small little magnetosphere to kind of pull in enough solar wind particles that they can interact with the atmosphere.
Really?
Yeah.
It has a magnetic field, a very thin
It has a magnetosphere. Yeah. I wouldn't say that it's specifically a field. I think that it kind of pops up here and there, but it has aurora belts, right? So yeah, here you go. Presence of these of crustal fields gives rise to local mini magnetospheres, small areas where the lines locally protect the planet's surface from electrically charged particles. So
wow.
Yeah, so they just kind of pop up, these little mini magnetospheres pop up on Mars.
Man, that's confusing. How do you have I'm just going to be a magnet right now?
Well, that's the thing with planetary science, right? Is we tend to oversimplify planets to things like Earth has a magnetic field, Mars doesn't. Jupiter has a huge magnetic field, its moons don't. We kind of say it's this all or nothing, when really one of the things we've learned from exoplanets is that properties of planets exist on a huge spectrum. And you can have massive planets that are incredibly close to their star, massive planets that are far from their star like we expect, right? I mean, we have, for the history of science up until about 30 years ago, we had one data point for what a solar system looks like. And that was our own. And we said, okay, small planets, rocky planets form closer to the star. The bigger gas giants form in the outer parts. And then we started finding planets around other stars. And most of them were these gigantic, larger than Jupiter worlds that were closer to their star than Mercury was to the sun. And that just kind of throws a wrench into everything. And over time, we've started to find different systems. And But we've learned that all of this does exist on this big spectrum, that solar systems are very different, and there are still laws of physics that govern how a solar system forms and how it develops, but we're still trying to nail that down.
That's the cool thing. I mean, think about the goal of science is to find single laws that describe everything. So the same physics that made our solar system will make other solar systems.
Mm-hmm. Well, and one other thing I wanted to ask you about, you were talking about some really great geomagnetic storms, like some of the big storms, because I want to know, like, why do people even care about this stuff? Like, what is the point? Like, why? Okay, look, we get a solar storm. People are talking about the power grid going down and like all this devastation. I haven't seen any of that.
It has happened. This very important stuff to know about. We need to understand Aurora not just because they're beautiful, but because we're living next to a massive nuclear bomb that shoots out massive solar flares at us. And as you say, and I remember you telling, I remember one of our shows, you were saying something about how if there was an atmosphere all the way out to the sun, then it would be like so deafening that it would bust your ears open or something like that.
Oh yeah, it's as loud as like a 747 right next to your ears. Or
something like that.
Something
anyway,
ridiculous. Yeah.
Yeah, solar flares affect Earth in a variety of ways. One of the ways is that moving magnetic fields and moving electric current can induce electric current in circuit boards, and so you can take out satellites, for instance, with our magnetosphere being pushed around. And that's happened. Mm-hmm. That happened back. There's been a few. So we've had, in terms of documentation, one of the earlier ones was 1859. It was called the Carrington Event, visible as far south as the Caribbean, where the Aurora.
With the auroras?
Yeah. And
oh my God.
Telegraph infrastructure was shocking people. So if you're one of those people on like the Morse code things, it was like shocking people. In the lines, the electric current, and there's even stories of people talking to each other through the telegraph. I think it was Boston and Maine or something like that, where the people doing the telegraph stuff, they unhooked their batteries. They had no electric source, and they were still able to talk to each other because the rolling magnetic field was inducing an electric current that they could use, that they could jump on. Oh my God.
I was laughing at that because I just think of somebody like operating a telegraph and he's going like does it I think it kind of mixes up the message a little bit. Yeah. But oh my gosh, the telegraph infrastructure went down, right? Yeah. So now the Carrington event, what year was that?
1859.
Okay, so 150-ish years ago. So, I mean, I don't think it's unreasonable to expect that we could get one of those in the next 150 years.
Not at all. And we've had other, like, smaller things. Like, we've had flares and magnetic storms in the last 20 years that have messed with satellites for a little bit. We've even had some that have created temporary radio blackouts. Even one this year, just over the summer, there was one, a solar flare that knocked out shortwave radio communication over the Atlantic in Europe for like 6 hours. So, and those are like, that's not even close to the energy that the sun has. If it wanted to, it could really, if the conditions were correct. If it wanted to, the sun.
It's alive. It really wants to screw us over.
It could do some damage, and so we need to understand the sun's mechanism. We need to understand early warning systems, and I honestly can't really say much after that because I don't think we can change our infrastructure in any reasonable way that would protect us against a major flare. I don't know what you would think about that, but
I don't know. It depends on how you can shield things from that. It depends on how we design our grid. I know in power engineering, there's smart grids are really popular right now, and they can reroute power from one part of the grid to another depending on where there's a lot of use. But that still doesn't tackle the problem of, the whole grid could get wiped out if you have a big enough event. For me, I guess the question is more about recovery. If this kind of thing happens, how do we protect the infrastructure and say, okay, we can handle this kind of thing without any permanent damage, or at least without irreparable amount of permanent damage, right? How do you are we guarding against something like this? Do we have some kind of backup system in place? Probably not. Or do we have some way to deal with something like this happening without losing a huge amount of infrastructure and throwing us all the way back to the Stone Age?
That is a fantastic question, Ryan. I have no idea.
Well, we just got to hope that it's not going to happen for now, I suppose.
I know that people do think about it, like professionals do think about this kind of thing. I don't know if anything active is being done. It's kind of like the asteroid warning, right? It's asteroids are something that's going to happen probably, and we need to figure out how to deflect them if necessary. But when are we going to start testing? Yeah,
it's true. Well, and you know, something like the Carrington event, I can't imagine Aurora being visible in the Caribbean.
I know.
Like at that point, you're pretty much like there's no magnetic field left. Like you're pretty much at the equator. You're getting there.
Yeah, because like it's super thin at the equator. Like that's an impressive amount of material being dumped onto the Earth.
That'd be cool to see, though. It'd be very pretty as we all cooked, as all the infrastructure fried, and it didn't make it.
There's so much to talk about on the Aurora subject. Like there's recent work that has been done on Aurora, the sound that Aurora makes, and it does make a sound. There's been Canada was the location of the first scientific proof of what causes the Aurora. It was a person out of the University of Iowa, State University of Iowa, but they were using Fort Churchill, Manitoba, to launch sounding rockets into the Aurora to prove that it was electrons, and that was the cause.
Wow!
And there's a whole citizen science group across the internet that just does regular people that go out and observe the Aurora and document really interesting things. We have no time to talk about any of that.
Or and the other thing that we won't talk about because we don't have time. Have you seen those the red flash, a sprite like a from the ISS?
Yeah.
They tend although those happen more above lightning storms, but I thought about them because they kind of, to me, they seem like a little bit like an aurora, a little bit.
Yeah, it's like sort of similar atmospheric emission features, you know.
Mm-hmm. Yeah, incredibly rare. But we'll leave that to the listener to go look
Google
that up. Yeah, and we should call it at that.
What are we going to talk about next week?
Oh, I have no idea.
Yeah, me neither. I meant to talk to you about this beforehand.
Well, that's okay. I mean, we've got lots of good topics to talk about.
Do we?
Cool. Till next week.
Well, that's the end of this show. Thanks for listening.
If you want to get in touch, find us on Twitter.
My handle is @JesseRogerson.
And my Twitter handle is @AstroInAction. Check out other episodes, or just keep listening to us every week.